Let's take a look at what's necessary for a chemical reaction to occur. This is known as collision theory. It's pretty straightforward. If a molecule is going to react, it must meet three requirements. Number one, there needs to be a collision. This could be a collision with itself, for example, if it's a decomposition reaction, or it could be a collision between two different molecules. They better collide with enough force to overcome the activation energy required. There's always some energy that's required for reaction to occur. Some things you really have to bake, other things take place nearly spontaneously. And they need to react at the right location. So if you're thinking in terms of individual molecules, you can imagine that some collisions are ineffective while others are effective. And knowing the reaction mechanism can provide great insight to that. As a practicing synthetic chemist, when you drew a chemical structure and it happened to have a reactant site, say you needed to remove a chloride from it and replace it with a hydride, with hydrogen. If that chloride was buried within the center of the molecule and surrounded by other stuff, you knew you were in for a tough time because getting to react in that location was not going to be easy. So those are the three things required for a reaction to occur. Energetically, if you looked at the energy versus reaction coordinate, which is really the same as time, right? This is from beginning to end. You'll see that you have to overcome some energy barrier in order for things to get going. It's typically endothermic overall. This spot right here is called the transition state. And for this reaction, it takes some energy going up here, but then you liberate a lot, and so it's overall an exothermic energy liberating process. Let's go ahead and listen to the video.
Let's analyze the changes that occur in energy and atomic arrangements as the reaction between nitric oxide and ozone occurs. Initially, the nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole.
Note that it is initially endothermic, and they only put the arrow right there because you get some of it back, right? This energy goes in, but it comes back out, so really that's a break even. The rest of it is all gravy, if you will. If it's a power plant, you're happy. This is how much energy you're liberating by this reaction overall.
Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the molecule
Notice that it has to smash like that. That's the only effective collision. Sliding things around wouldn't matter. Ozone being ridiculously symmetrical, and they're drawing it as almost a trigonal structure. I don't think it is, but assuming it is, that's what you're looking at there.
are in a transition state or activated complex,
right there.
the potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state characteristic of the products.